Okay, good morning, everyone. Today we have Ece Takmaz with us. She is a PhD student at the Institute for Logic, Language and Computation at the University of Amsterdam, and she is also a member of the Dialogue Modeling Group supervised by Requia Fernandez and Sandro Pazal. And today she will talk about their EMNLP paper on using human gaze to guide image generation. So the stage is yours, Ece.
Thank you. Thank you very much. So today I will be talking about this paper first, about the generation of image descriptions guided by human gaze. And if there is still some time, I also want to briefly touch upon the other paper that we had to give you kind of an idea of what kinds of things we are working on in my group. So I will start with generating image descriptions via sequential cross-modal alignment guided by human gaze. And this was done in Dutch, so it's a bit of a different language, which is lower resource, but it was an interesting challenge for everyone involved. So image description, when we are describing an image, there is a complex cross-modal coordination between visual processes and linguistic processes. So here we see visual processes here in the first row, like looking at some parts of this image, and someone is describing this image. So it's the linguistic production is kind of described, it's shown here. Our eye movements are affected by the task. So here the task is to describe the image, but if the task was to, let's say, search for the pizza or something like that, our eye movements would have been probably a little bit different than what we see here. And then this in turn affects what we produce at the end. So it's like, if you look at the people first and then look at the pizza, and then, so it may have an effect on our linguistic production at the end. So inspired by these findings, we wanted to use this data set in Dutch, which they had images and spoken image descriptions, along with concurrently collected eye tracking data. So when people were talking, also their eye gaze movements were also recorded. So using this data set, we first analyzed the data set to see the alignment between these modalities and to what extent there is this sequential alignment between visual and linguistic parts of the data set. And then we proposed the first models that use speaker-specific sequential gaze in the generation of image descriptions. So we believe that this is, the results could be informative both for AI and for cognitive science. And so it's interesting case of using gaze in this task. So why are we using gaze? Gaze has been seen as a proxy for attention and as a proxy for the contents of underlying cognitive processes. And these are generally reflected as in fixation. So they are slower, more stable eye movements that we can see here like as red dots. Gaze has been used in computer vision for saliency detection and object segmentation and various other kinds of tasks in the form of a saliency map that we see here. So it's usually a single static map that is an aggregation of everyone who looked at this image, for instance. So it's a single format thing. Gaze has also been used in NLP for part of speech tagging, for parsing, for reference resolution. I think usually inspired by reading studies. So there are lots of studies on reading that they use in eye tracking. And here as well, it's kind of only text and some kind of, like for these ones, usually it's just attention over text. Here we again see that gaze is used in an aggregated manner. So maybe we have average fixation duration for a single word over all participants who read this sentence, for instance. But gaze is actually sequential in nature. So it's speaker specific and sequential. So for instance, when we are looking at an image, we tend to look at an object just before saying its name. So there is some kind of an alignment, but this is not utilized in any of these studies. So that's why we wanted to use gaze, but in a different format than previously it has been used in this manner. So I will continue with our research questions in this study. So the first one was, there is this cross-modal alignment between vision and language, but can we capture it better using gaze in a sequential form rather than a static form? So this could help us leverage things that were not used in previous work before. And then we wanted to see if using speaker-specific representations instead of aggregating over multiple participants, would this help us? And again, here we have this more fine-grained data, again, not like aggregated in any way. And finally, we ask, would incorporating speaker-specific gaze sequentially allow us to generate more human-like image descriptions? So human-like here is about the semantics of the description and the sequence of the description that I will tell you later. So I mentioned this data set. This is the Dutch image description and eye tracking corpus, DIDEC, which was actually not collected by us. It was collected by a different group at Tilburg University. And so here we see an image, and on average, there are 15 captions, descriptions per image by different people. And again, as I said, there's the spoken descriptions and eye tracking data for each of these descriptions. So what we did was to take the audio files, and they had these automatic transcriptions that were later manually corrected by the annotators, but they didn't have timestamps for the words themselves. So we first obtained the timestamps for the words using forced alignment tools. And then we started aligning the fixations with the uttered words. So let's say this is the first word. Before this word was uttered, there were some fixations that were made on the image by the speaker. So they were just looking at the image and thinking of what to say. So we combine all of these fixations, and here you can see, let's say they looked at this part and this part. So we obtain these masks. For the first word, it's like that. And for the next word, we look at the onset of the previous word. So from this part to this part, what has been done. And then it goes on until the end. And for the fixations, you can see they're kind of like Gaussian distributions. That's what we did. So we take the fixation centroid, we fit a Gaussian around the fixation centroid, and the standard deviation is 1 degree of visual angle, which was 44 pixels in our case. So for every fixation in this window, we have this. And then we did this for every word in the description. And in this way, this data set allows us to delve into the process of generating a description and not just the end result of this. So we know where people looked at while they were generating this description. And then we use these masks, and we mask the original image with these masks, ending up with these sequence of kind of masked versions of the same original image. And then we use ResNet to obtain the features for each of these. So these were sequential speaker-specific masks, but we also had the non-sequential aggregated masks. So this was like the analogy to the saliency maps in computer vision. So it's just finding out the maps for every participant who talked about this image and combining all of these into a single static map. We also looked at the data set in a different format to see how much cross-modal alignment there is. So we assume there is some alignment, but what is the extent, or like what kind of an alignment there is? So we conducted a cross-modal correlation analysis. We represented the fixations as like a scan path of objects. So people looked at person, table, pizza, person, knife, and so on. And then we have the description. So I'm not going to go into detail now about this, but what we did was to compare the scan paths with each other and compare the sentences with each other. So having this pairwise similarities and then ranking them and then seeing the correlation. And we found out that if we represent these in a sequential manner rather than, let's say, bag of words, this explains alignment better, but still it's slightly more intricate because we don't always say what we're looking at. So we're looking at the table, but we don't mention it maybe in the caption, or like there is knife, but we don't say knife, but maybe it's kind of implied here in eating, fork and knife and so on. So this alignment is more intricate, and it actually contributed to one of our models, this idea of having some intricate cross-modality. So I can continue with our models now. We based our models on the bottom-up, top-down attention model by Anderson et al. This was already influenced by the ideas from visual processing in humans. So we have the bottom-up processing and top-down processing of the image. So here we have these bounding boxes, which are the bottom-up, which is at the end result of applying bottom-up attention over the image. So it's salient parts or maybe novel parts of the image that are driven by the visual stimuli itself. And the top-down attention depends on the task. So our attention over the image given, let's say, the task is to describe the image versus the task is to search for something in the image and so on. So we first did this bottom-up, top-down attention model, and it's the no gaze model, as we call it, because here we don't give any gaze input. We use the model as it is. And here we have the, let's say this is the description, and we will output words. Here the visual input is the mean pooled vector for all of these bounding boxes. So we have the features for 36 bounding boxes, and then we give the mean pooled vector as input to the model. And here we have the top-down attention LSTM, which will learn to apply top-down attention over these different sized boxes. We have the language generation LSTM that generates the words. And in the middle, we have the attention module that learns to attend over these boxes. So in our models, we don't give this V hat, but we replace it with the gaze-based, gaze-conditioned images. So here we have the gaze ag model, where we give the image masked with the aggregated map. So at every time step of the generation, we give these exact same features to the model as input. But in the sequential model, at every time step, we give a different feature vector, because we have this speaker specific and sequential input that now we can give to the model as GT. As I was mentioning, there could be a more intricate alignment between the vision and the language modalities. So we wanted to add this extra gaze LSTM. So this LSTM only takes in these image features and outputs a hidden state. And instead of the gaze features being directly input into the model, we give this hidden state at every time step. Again, it's a different vector. So one thing I should say here is that this data set was really small, so it only had 4,000 captions. So for this reason, we actually machine translated the MS COCO data set, which is in English, into Dutch. And we first pre-trained the model on this MS COCO machine translated data set. And then using the weights of this pre-trained model, we fine-tuned this model, all of these models with gaze. using the DDEC dataset. So it was a two-step approach to training here. So I want to talk a little bit about this metric that we proposed. So in our paper, if you look at it, we also report other metrics such as CIDR and BLUE that have been used in evaluating generation models for quite a long time, but they could be capturing other things than what we're looking for here. We were specifically interested in the semantics and the sequentiality of the generated descriptions. So we propose this SSD metric, which looks at, let's say, this is the generated sentence and this is the reference sentence. And we actually calculate this score from two directions, from G to R and R to G, and we take the average of these two directions. So what happens in one direction here is that we use word embeddings, pre-trained Dutch word embeddings. So this is just a toy example. To find, let's say here we go from the generated to the reference sentence. So we found for each of the words in the generated sentence, the semantically closest word. So here A is exactly here, lovely, maybe close to nice, and cat is here, lying, etc. So for each of these words, we find the semantically closest word in the others on the other side. And this will give us the embedding distance. But then we also see there is a sequential distance as well. So here A is on the same position, but like sofa is here, but couch is here. So there is some positional distance here as well. So we also add up a relative positional distance into the embedding distance. So this whole thing, that we add everything up and we end up with a single unbounded value, which is a distance score. So it's the lower, the better for us. And we do it from both positions and we take the average value to see how aligned the generated sentence to the reference sentence, let's say, in terms of both semantics and the sequence. And we wanted to have this because we are interested in gaze and language alignment, but also how we generate things. It's also important to see how aligned they are in what we're looking for. So I can give you some scores here. Again, lower is better. What we see first is this is the average of 5 runs, and these are the standard deviations. We see that the gaze models tend to have better scores. They are lower, especially the sequential models. And they have, the gaze models also have lower standard deviations. So from this perspective, we can say that the gaze models actually generate semantically and sequentially closer outputs. They are more human-like than the other models. And our best model was the model with the extra gaze LSTM, where we added this other level of processing. Of course, these are the scores for our metric. You can take a look at our paper for the scores for CIDR and BLUE, which they also made quite a lot of sense in terms of having this order in the models. We then looked at the test set generations. For every image in the test set, we generated sentences with all of the models, picking the best model per model type. We didn't see a difference in sentence lengths. They mostly had similar sentence lengths, but we see a difference in vocabulary sizes. So the gaze models generated sentences that incorporated a more varied set of words, especially the one with the extra LSTM. And then we also saw that gaze to sec, the one with the extra gaze model, generated the most varied set of descriptions. By definition, the no gaze model and the aggregated model, they only generate a single description, but the sequential and speaker-specific models also allow us to generate various descriptions for a single image. I will now tell you a little bit about some phenomena that we saw in the generated captions. So here we have the no-gaze model and the model with the extra LSTM. And in the second model, we usually see more specific captions. So instead of just saying a woman standing in the kitchen, it mentions the donuts, maybe like they're rather small, but it's a specific thing for this image, which also contributed to the vocabulary size differences. And we see this overall for other images as well. One interesting thing was disfluencies. So in the data set, there are annotations for these filler sounds, like that indicate some hesitation on the side of the speaker. And we actually opted for keeping these in, and we saw that the 2sec model actually generated these as well for this image, and we went back and looked at the references, went back and looked at what people said, and indeed they were also uttering these filler sounds. So we speculate that there could be something in the gaze modality that gives us like a hint about cognitive load or some uncertainty about this image, some hesitation in the image. So when we look at this image, maybe it's like there are some birds and some traffic lights, but it's not as specific, like we can't maybe explain it as well as this image. There is some maybe confusion, and this could be reflected in the gaze modality. Of course, the idea of generating these fluencies is a little bit debatable, because this is not a very good description for this image per se. We may not want to have disfluencies like this, but this is what the humans did. And if we want to have more human-like descriptions, it would be good to keep these in dialogue as well. Maybe we want, let's say there is a dialogue model, we want it to be able to chat in a more human-like manner, then we should keep these kinds of things that are human. So then there was this last thing about compression, and here we see that the no-gaze model, it says like a red bus and a bus, and it repeats some things, but the other model, it actually compresses, so it's 2 buses that are parked, which is a nice way of explaining this. This repetition is, of course, if you have worked with language generation before, occurs in the early stages of training, or maybe the model is not trained well enough. So there are such things that occur, but in our second model, we see that it is able to overcome this. Yeah, so I think to conclude, we have used eye tracking coupled with language production as a guide to image description generation. We have seen that using sequential gaze data as opposed to static gaze data can help us generate more human-like descriptions. And again, having the speaker specificity versus aggregated gaze, it can help us capture more fine-grained things and allow us to generate multiple possible descriptions for a single image. And this was a novel approach, making use of real human attention, generating relatively diverse and more human-like descriptions. So of course, there could be other things. So if we think about Turkish, for instance, we have a very flexible word order. So maybe the sequentiality and the alignment would unfold in a different manner. And we are still really curious about what this extra gaze LSTM contributes. So what is it that it represents, that it contributes to this model to have more human-like descriptions? So there could be some work to be done there. And maybe one final thing is that here we assume that the gaze is given and we only predict the words. But it would be also good to predict the gaze along with the uttered words to make it even more human-like, or to make it independent of the gaze data availability and so on. So here we show that leveraging cognitive data in computational approaches could be a good way to go, and hopefully opens up the door for further work in this direction. So I have the link to our GitHub repo here, and I can take some questions now, if I have time.
Thank you, Ece.
Yeah.
So, any questions?
I have one. Nice presentation, thank you. Recently, Google or someone else released a database of speech and mouse movements, right? You probably know. How does that, did you look into that? And how does that compare to the eye gaze database that you have over here?
I may not be familiar with the recent dataset of Google, but there have been some previous datasets, maybe Silicon, I guess, with mouse tracking. And mouse tracking is kind of, it is seen as a replacement for eye tracking, but it doesn't, I think, correspond directly to eye tracking because it's not as automatic. It's a different motor movement, but of course it gives us information about where people are looking at. So it's a good proxy for eye tracking, especially if you want to collect eye tracking data, there should be some eye tracking devices or webcams and so on. So having mouse tracking is a much more feasible way to collect this attention data. And I guess it's probably a much bigger data set. I didn't look at it, but I would be interested in seeing how it would work actually. Yeah.
All right.
Can I ask something?
Yeah.
Is it? Thank you. It was a very nice presentation indeed. There is some part that I maybe somehow missed this. So you somehow use the uttered language, right?
Yes.
In your system, but I couldn't get how you incorporate it to your final system eventually. I mean.
So let's say this model here.
Yeah.
So this is a language. It's a language generation LSTM. So we started off with start of sentence. So this orange box actually. So yeah, maybe I should have said it. So we are not using the speech or audio, but we're using the text. So yeah, maybe I wasn't clear there.
And you were talking about fixations and such things. So for that you need audio, right? For
the fixations, so here there is the audio in the data set.
But you don't use it?
No. We only take the timestamps, like the milliseconds, and then we align them with the fixations so that we know before saying this word which fixations were done. And then we kind of discard the audio. Yeah, we didn't do, but I think it could be a good way. I have never done audio processing or never used audio in my models. So it's not exactly audio visual, but text and vision. So it's tokens.
Yeah, so here the fixations are important, or timestamps.
Yeah.
So it's important when the words were uttered, but it might also be, I don't know, relevant how the words were uttered, right? So that might affect also the semantics of every word that was uttered. How it was uttered affects also maybe meaning.
Yes, so that's really good point, because sometimes maybe they are unsure, and actually in the data set, because they are speaking, there are some corrections. Sometimes people say something and then they say, oh no, I actually wanted to describe it like this. So
they hesitate, right?
Yes, exactly. So there are these hesitations, there are corrections and repetitions, and some of these are annotated explicitly in the dataset as well, in the text form. But giving it in the audio form will also be really helpful. Maybe someone is not so sure about their description and so on. I never did that, but it would be nice to directly give that input to the model rather than having this more discrete version of language. Yeah.
Okay, thank you.
Thanks.
So Ece, I have a question which is somehow related to Metin Hoca's question. So in the Silicon dataset, for example, which collect these fixation through mouse interactions, they provide a blurred version of the image. And when you just click on a particular region, you see it's in full resolution. But here, in the way you feed these regions, you take the fixation, you just use a Gaussian mask, and then you zero out the surroundings.
Yes,
Your model, in that sense, are not used the full extent of the image, or somehow maybe.
Yes, you're right. Yeah, so that's one of the differences. So here, for instance, again, it's not using the full image directly, but it's using these like bottom-up regions and gives the average of these bottom-up regions. But in our case, we zero out these parts, and this was something that we discussed actually, to keep the blurred parts instead of having a black outline. And I actually tried the blurred version, but it didn't give us better scores. And this was also one thing that we wanted to kind of replicate, was that when we're to kind of have the objects more stand out, like rather than having, because when we blur the image, we can still maybe guess that there is a person here or like so it was more to have a very specific object input, maybe not like these bottom-up regions, but kind of in a way to keep it. But I think it's worth giving another try, that I can maybe try it again in a different form with blurring.
Like you said, there is a trade-off, but in this particular way, you are basically losing the global context.
Yes,
so that's why
but we still keep the bottom-up regions here, the attention. So the idea is, so maybe I should have made that clear as well. So the bottom-up regions are still there. So what we kind of change is that giving this input will influence the attention over the bottom-up regions here, hopefully. So that's still there, but the input, but there could be like various ways of combining the input. We can actually give the full feature vector for the image as well. Maybe it could have been better even,
And like another follow-up question. So here you are feeding these salient object regions obtained from the fixations to the model. Can you try, or did you try, like maybe just provide just the first fixation, or just the first two, the first three, and how that affect the final prediction?
So only giving the very first fixations on the image? Yeah, we didn't do that actually. I never tried it. But one thing that was actually interesting in the data set is that some people, when looking at an image, start talking immediately. They start describing the image directly. But some people just take a look at the image, wait for a while, and then they start talking about it. So there is some work in psycholinguistic literature about like they're taking the gist of the image and then they're talking about it. So there is this difference. So one thing that could be further researched is how are these approaches different? Like if we start describing immediately versus if we take some time and then plan what we're gonna say and then produce the language. So it's maybe having the first few fixations for people who waited for a while before talking could indeed be enough. But for the ones who start immediately, they may still need to do some more fixations. Yeah, that would be.
Actually, I was gonna ask that as a follow-up question. I think this framework is also really interesting to apply in a, let me say, real-time setting. Like there are these current some real-time machine translation frameworks where you see some source words and then generate some words in the target language, and then maybe just wait for more source words. So maybe you can also adapt this framework to this more interactive setting as well. That would be
yeah, that would be really interesting. And I think that in that case, having this maybe gaze prediction could also be helpful, like simultaneous, without waiting for people to look at things, maybe predicting already from the start where they could look at or something. Some simultaneous, yeah, that would be really interesting.
Thank you. I think we have a question from Omar. Yeah, go ahead, Omar.
Yes,
You can unmute yourself.
Thank you, Ece, for the presentation. It was very good insights on the topic. So as far as I understand, you are trying to minimize the sequential distance between the ground truth and the reference description. I might be wrong, but let's say, as an example, in the example you mentioned, I am, as a person, more interested to mention the cat first instead of the couch, the color of the couch. So does this affect the generality of the model, like this approach? Because both descriptions are correct. So in terms of generality.
Yeah, so I think when we look, because we are looking at speaker specificity as well, we are losing some maybe generalizability of the descriptions, because we don't want to have the very best description, but to have different kinds of descriptions that could fit this image. And yes, it depends on what people want, how they said the things. Maybe for an image, there was a pattern, everyone said it in a very similar way, but for a different image, they had a kind of a different approach to describing the image. But of course, this whole evaluation of the generated text issue is quite still an open issue, actually. Like, how do we evaluate it? Because as you said, both of them are correct, they are not wrong, but there is a distance between what people said, and there is always this thing, like, I think in this case we had 15 descriptions per image, but what happens if we had only single description per image, for instance? So it's a bit of a trade-off that we have to do here, and we kind of accept that it's not going to be able to capture exactly right, like the correct caption. But yeah, I hope it answers your question.
Yeah, thank you very much.
There's still, I think there's still lots of I still see these like language generation metrics coming up. Like recently there was BERT score, for instance. They are using word embeddings in a way that kind of also mirrors precision and recall and F1 score and so on. But it's still an open issue, especially, so in my group, if I have time, I may also tell a little bit about the dialogue bits that, so that's also an issue in evaluating dialogue generation, because we only have a single example of a dialogue. And how do we even say, here it's just a single sentence, but in dialogue generation, it's an ongoing process. And it's like, it could go to a very different part of the space as we talk about things. So maybe I can move if that's possible. We
have 15 more minutes.
Oh, okay, good.
Maybe before switching to the other topic, I can just quickly ask one follow-up question.
Yes.
So overall, performance analysis with gaze, without gaze table you have, the differences are, I mean, looks small, but have you checked, for example, the significant divergence of no gaze versus gaze models at the generated sentences? Do they significantly differ for some and maybe significantly worse for other? over that?
So yes, this was a thing that we also discussed in our group, because these values are really close to each other, and we weren't sure if they really reflect what we were looking for. But when we also look at the cider and blue scores, we saw a similar distribution, but maybe with like a higher distance between the scores. And that's why we actually did all these analyses looking at the generated descriptions to see what is the difference, like why do we have okay, this is a small difference, but what do we have? So I can at least tell you that the vocabulary sizes were very different. So the gaze models, especially this one, had a vocabulary that was closer to human levels. So I think it affected the generated descriptions, the quality of the descriptions, and the semantics. So, but I don't have any significant statistics that I can tell you about. It was more an observation.
Yeah, thank you.
Yeah, thanks. So there was this one final thing that I wanted to mention. This is about generating referring utterances in visual and conversational context. This was a second paper that we had at EMNLP. And here we used the PhotoBook dataset that was also collected in our group. So I think the idea of it is, I can mention it like that. So let's say we have this image and we're talking about this image with a conversation partner. We could start by saying a white fuzzy dog with a wine glass, and then the other person maybe says, oh, I see the wine glass dog again. And so it's if we see this image multiple times, the way that we refer to this image could change over time. Let's say we were talking about this image with different people, then we may just start with white dog sitting on something red, and I have the dog on the red chair. So it's a whole different phrase that we see here. So we're looking at referring. So we refer to this image, and then we reuse what we used to refer to this image. And there is this phenomenon that people reduce things as they go along the dialogue. So instead of saying this longer phrase, maybe they will just say, oh, it's the fuzzy dog, and so on. So there are these things that we see in dialogue. It's quite a lot studied in linguistics. And the idea of this PhotoBook dataset was also to capture these. So I have this kind of toy example from the dataset. So there are two participants. They don't see each other's images, but they have to determine which image they have in common. So they talk about, oh, I have the white cake, I have the guy taking a picture, and so on. So this is round one. And then let's say they decide, oh, we both have this guy taking a picture. And in round two, they will have different images, but some of these images will come up again. So they will be talking about the images again. And we wanted to see how this unfolds. And let's say this image comes up again in round one, and then in round two, and round three. So every time they're mentioning it in a different way. So, so this data set captures this conversational common ground and how people build this references to previously seen images, and how they generate new utterances for this image. And in our paper, we are looking at generating these utterances. So we have this chain of utterances for a single image. So we're looking at generating the next one from the previous ones. And I can maybe quickly show you. So this was our base model that takes the visual context and the target image, and then generates an utterance for this target image, only using the visual context. And then in our second model, it is the re-referring of the, okay, so maybe I can tell you. We have the visual context and the target image, but now we also have a previous utterance. So here we use like the history of the dialogue, how we talked about this image before, and then generate a new utterance for this image. And we also have this copy model, which is based on a pointer generator network. So it combines the probability of generating a word from the vocabulary with the probability of copying a word from that is being from the previous utterance. So this is again building our generation on previous history, but in a different manner. And we saw that having this conditioning on the previous utterances, it makes the generation of the next utterances much better, more human-like. We checked this using Bird Score and Blue and Cider and so on, but we also did something different where we looked at this from a reverse perspective. So if we give this generated sentence into a resolution model, will this generated sentence be able to pick out the image? So it's not the generation task, but it's the resolution task. And here we also saw that the generations by the, I think it froze. Generations by the models that condition on previous utterances, they are also better at the resolving of the image. So given this caption, utterance, what is the image and so on. So this was a way of kind of modeling conversational history along with the visual context and how these processes will unfold again in a more sequential manner over time. So I just wanted to mention this really briefly because we are interested in dialogue in my group and conversational research, and I'm especially interested in the multimodal systems of vision and language. So if you're interested, I think this is the link to the dataset, and you can find several papers that come out of this dataset, and this is the group that I belong to. I think that's it from me. I can take even more questions if you have them.
Thank you, Ece. So maybe we can take one or two questions.
So I didn't look
Any
at the chat, but okay. I didn't see anything.
So any questions, especially from our students?
Thank you, Ece, for the nice two presentations, actually.
Thanks.
So at one point, I think in the first part, you mentioned that some languages are more flexible, like Turkish. So I wonder, depending on the being like a direct speech or indirect speech on a language, does it have some sort of print in the gaze? Like just by looking at, okay, Turkish is, for example, assumed to be a language which is kind of flexible and you can easily change the intention and even the complete meaning of a sentence from where you start and from where you end to where you end. Does it have a sort of signature in the gaze as well?
Yeah, that would be really interesting to, I don't know, but what I could think is that maybe from the other direction, it could be like, let's say we look at an image and in Turkish, because we have this flexibility, we can start by saying directly what we're looking at. Like, oh, there is a car, blah, blah, but maybe in like in English, for instance, first you have to say some subject and then like, I don't know, auxiliary verb and so on, and then comes the object. And so it's maybe the constraints of the language could be, yeah, I think it could be interesting. I am not familiar with that line of research, but I definitely see the value in doing similar studies for different languages. Yeah.
Because at one part, like you said, like some people wait for a while and you do the fixation and then continue. Is it just like a variability with respect to people, or also the language itself has
Yeah,
such
yeah, maybe that also could be different. Yeah, maybe if we look at people, yeah, maybe let's say for Turkish, maybe we will have a shorter span. We will just start talking directly without thinking about saying other things. Maybe the planning part will be different. But I think, at least from what I've seen in this data set, it was mostly speaker variation, like for some people, because there was no instruction given to them. There was no time limit. You can take a look at the image, you can talk about it whenever you want to talk about it. So it was a personal choice that they did. But I think maybe one thing that could be interesting as well, if there are people who do computer vision, for instance, maybe it's about something in the image that makes it complex. Somehow the scenery that we see is rather complex to describe. So most people first just try to take in what is in the image first and how to do. So it's a bit of an interplay between the objects in the image, the complexity of the image. Maybe there are some really weird objects in the image and you can't find a label for them. So you can't immediately know how to describe this image. So it's quite a lot of things at play here. So yeah, very complex.
So maybe I can jump in here, Ece. So there is a paper from David Parik's group. I think the title is called Image Specificity, where they analyze whether given an image, humans can describe this in a more similar way each time with different subjects, or that each person can just write down a completely different description. That's also related to the complexity of the scene.
Yeah. I've seen recently some work using scene graphs, and it's also another way that we can look at. So if we have a scene graph of an image, maybe combining it with eye tracking data could also be quite interesting, and also comparing the scene graph to what is being generated at the end. Maybe the more complex the scene graph is, you will have like a more complex description at the end, like more relative clauses, more, I don't know, lots of things could be researched here, and not just for like AI and computer science, but for cognitive science as well. Like I was mentioning at the beginning, this gives us a way to have maybe better descriptions, better understanding of vision and language, but also on the other side, let's say the aggregated models didn't produce more human-like outputs. So we can say, okay, maybe the sequentiality is more important in human cognition as well. So we can say things for the cognitive sciences as well. Of course, not a proof of anything, but just as a like a hypothesis or an idea of what could be going on.
Okay. I think the time is up. So thank you, Ece, again for this really interesting talk.
Thank you.
We would like to see more on these topics from you and your group.
Thank you very much. Thanks for the invitation. I'm really happy to be able to meet and see all of you. And I would be happy if you would like to contact me about the papers or data sets or anything. I would be really happy to hear from you again.
Thank you, Ece.
Thank you.
Thank you.
Thank you.
Thank you, Jawad.
Bye.
Okay, bye.